Ever wonder how scientists determine if an AI model is truly reliable at making predictions? It's not just about being right, it's about how accurate and confident those predictions are. Today, we're unpacking two critical metrics in machine learning evaluation: Hamming loss and the Brier score. These tools don't just measure success, they reveal the quality of success. Let's dive in. Starting with Hamming loss, a metric designed for multi-label classification tasks. Imagine a model analyzing a satellite image and identifying multiple land types, like forests, urban areas, and water bodies. Hamming loss calculates the average proportion of incorrect predictions across all labels. For example, if a model misclassifies 6% of agroforestry areas in a dataset, that's a Hamming loss of 0.06 for that class. But here's the catch. If another model gets 45% of arable land predictions wrong, its Hamming loss jumps to 0.45. The lower the score, the better, because it means the model is minimizing errors across all categories. Now let's shift to the Brier score, a metric that evaluates probabilistic confidence. Think of it as a report card for models that output probabilities instead of binary answers. If a model predicts a 70% chance of rain, and it rains, that's a good prediction. But if it doesn't rain, the Brier score penalizes the model for overconfidence. Mathematically, it's the mean squared difference between the predicted probability and the actual outcome. A score of 0 means perfect calibration, like a weather app that's always 100% accurate. For instance, MOS-AI-C1 achieves a Brier score of 0.12, while models like ConvNext or RaiseNet struggle with scores above 0.2. This isn't just about accuracy, it's about how trustworthy the model's confidence is. Why do these metrics matter? Hamming loss exposes the frequency of errors in multi-label systems, while the Brier score reveals whether those errors are due to miscalibration. Together, they form a comprehensive evaluation framework. Take Earth observation, where models analyze vast datasets to detect deforestation or urban sprawl. A low Hamming loss ensures the model isn't missing critical labels, and a low Brier score confirms it's not just guessing, it's reasoning with precision. Here's where it gets fascinating. MOS-AI-C1 excels because it focuses on the right features. Its heat maps highlight critical details, like the texture of soil or the density of tree canopies, while other models wander aimlessly, like a detective chasing shadows. This isn't just about raw performance, it's about interpretability. A model that's accurate but opaque isn't as useful as one that's both precise and explainable. So when you hear about AI breakthroughs, remember, the best models aren't just smart. They're calibrated, precise, and honest about their uncertainties. Hamming loss and Brier score aren't just numbers, they're the lenses through which we judge the reliability of AI. What do you think? If you had to trust an AI with something critical, like climate monitoring or medical diagnostics, which metrics would you prioritize? Drop your thoughts below, let's keep the conversation going. Thanks for watching. If you want to explore how these metrics are calculated or see real-world applications, check the description for links. Stay curious, and we'll see you in the next video.